The third talk this morning will given by Professor Kim from Korea Institute of Advanced Study. Professor Kim is a professor of School of Mathematics at the KIAS. He is a fellow of Korea Academic Science and Technology. He was awarded the Korea Science Prize in 2008 and was an ICM United Speaker in 2018. He was also a member of ICM 2014 Program Committee and a former president of KIS. So now let's welcome Professor Kim to give a talk on complex algebra surface with PG0. Okay, so let's welcome.
Thank you very much for introduction. And first of all, I'd like to thank the organizers for inviting me to have a chance to talk here. Well, my title is slightly changed. I didn't have much idea what who are the audience when then. And also this morning, Virkar gave a nice talk on Fano geometry. So my talk will be more focused on dimension 2. So maybe some of the students might be interested in this. And so this place is quite impressive with very nice campus and with the young students and young mathematicians. Okay, so my talk is based on two papers, mostly jointly with Kyung-Suk Lee, who is now in postdoc. Number one is combinatorially minimal Mori-Dream surfaces of general type. And second one is examples of Mori-Dream surfaces of general type with PG equals 0. And in the meantime, I'll talk about a little bit about fake projective planes and so on. And so basically our question was which surfaces of general type with PG equal Q equals 0 are Mori-Dream. So I will define Mori-Dream later. But being Mori-Dream is that the surface the variety has very nice cones, effective cones, left cones, semi-ample cones, and rational polyhedral, so that you can do contraction a very nice way. And what are their combinatorially minimal models? And what kind of singularities on a combinatorially minimal model? And then how many? So we'll answer some of these questions. So let me start with rational surfaces. A smooth rational surface has a minimal model, not necessarily unique, which are P2 or Hirzebruch surface Fm, and it's not equal to 1. Well, usually surface theory, we are done here. We don't go further usually. But Fm still have negative curve, so you can contract. So what I call a combinatorial minimal model is one of these, P2 and F0, P1 cross P1, quadratic, smooth quadratic, and a cone over a rational normal curve of degree m. So P2 and P11m has picard number 1, and P1 cross P1 has picard number 2. So for rational surfaces, the combinatorial minimal model is rather simple. But as you see here, the picard number is equal to 1 or 2. And can you say something similar for surfaces of general type in P equals 0. So in fact, surfaces of general type with PG0 has been extensively studied for many, many years, but not yet completed. The classification is far from being completion. So this is somehow to understand these surfaces. Well, these surfaces still examples are lacking for some given invariants. So let me start with the first example of surface of general type, kind of traditionally well-known, classical, one of them, classically known. So Brunner surfaces are minimal surfaces of general type with PG equals 0. They are constructed by Brunner in 1966, about 60 years ago, as a bi-double cover of P2 branched on 9 lines. So this Galois cover, you take the double cover first on some part of branch curves, and then double cover again, branched along the image, pre-image of the remaining branch parts, branch lines. And these 9 lines, a triangle plus and 2 more lines at each vertex. And first double cover is branched along the 6 lines here, except these 3. And then the second double cover. So and looks like these 3 points should be blow up here. And of course, also you can have at the first double cover, this will give you a singularity node. But the second blow up, this point will be included in the branch. So upstairs you'll get smooth point. So this will give you a node, and then next blow up smooth point. It doesn't matter much. And also, in special case like the 3 of these lines meet at 1 point, and then you have to blow up that. So in this case, you get pickup number 4. So depending on the configuration of the 9 lines, K-square can take value from 2 to 6, and pickup number could be 8 to 4. And let's consider the simplest case, the Brunner surface with K-square equals 6, which means that pickup number is equal to 4. And they are called primary Brunner surface. This one has 6 negative curves, which are smooth elliptic curves, so with self-intersection -1. This means pickup number is 4. This one has 6 smooth elliptic curves. Forming a hexagon, or -1, but yeah. All smooth. And effective cone is generated by these 6 curves. And in this case, left cone is equal to semi-ample cone. kind of Neff cone is kind of dual or effective cone. And generated by, you see, these two are any kind of two adjacent curves is self-intersection 0. And numerically equivalent to kind of opposite pair. So we have 3 fibrations. If you pick up 2 fibrations out of these 3, this will define a map from X to P1 cross P1. And then you can think about Stein factorization. Then the second map is a finite morphism. First map is a contraction. So this X0 we'll call a combinatorial minimal model. This is quite similar to the rational surface case. Here, P1 cross P1, but for surface of general type case, well, whenever you have a 2 fibration, always you have a map to P1 cross P1 and Stein factorization, but not necessarily you get combinatorial minimal model because the map may not contract any curve. But in our situation, so it is the case. So for this primary Brownian surfaces, there are 2 combinatorially minimal models with Picard number 1. So you can contract. If you think about the linear system, certain linear system, a multiple of this linear system contracts 3 curves. This one, this one, this one. And then you can think of another one. So you get Picard number 4, you contract separate 3 curves. So you get Picard number 1. And this linear system, certain multiple, this one contract 2 curves. So if you pick up this one and this one, then this is common, so it will be contracted. And also this one is equivalent to this numerically. And also this one is equivalent to this. So E3 is contracted. So see, yeah, the 3 curves contracted or the 2 curves contracted. So you get 2 combinatorially minimal models with Picard number 1 and 3 combinatorially minimal models with Picard number 2. And all of them have simple elliptic singularities. So the situation is not so bad. We don't get very bad singularity here. Well, it turns out that the Brownian surfaces are Mori dream. And every Mori dream surface has a combinatorially minimal model, which is a Mori dream surface. Of course, some surface which may not be a Mori dream could have a combinatorial minimal model. a combinatorially minimal model is cube factorial and projected. So you can contract suitably choose negative curves always to a normal point, as long as the negative curve intersection form is negative definite. So, but this is analytic. So, I mean, the resulting surface may not be projected. This is the problem. So we always keep during the contraction in the category inside the category of factorial and projective. So every step we keep this. A combinatorial minimal model has Picard number at most 2. And if it has Picard number 2, then there is always a finite morphism onto P1 cross P1. So this is the general picture. So how we do this? So here, to guarantee that you have a combinatorial minimal model, we should work inside Moriddin spaces. Of course, if you start with non-Moriddin surface, you may get a combinatorially minimal model, but not guaranteed. So okay, let me begin with the definition of Moriddin. So for a normal variety, a Cox ring is the sum of all sections where D runs through a class group. And if this Cox ring is finite generated, X is called Moriddin. It was so called by E. Hu and Sean Keel. I hope Professor Mori liked this word. He just left for Japan, going back. So here we need class group should be finite generated. Otherwise, this ring is too big. Or equivalently, irregularity Q should be 0. So we will always assume that irregularity is 0. So in dimension 1, a curve is Moriddin if and only genus equals 0. Assume that irregularity is 0, then we have this inclusion, semi-ample, it's movable, it's closure, and it's nap. For surface case, this is effect that they all live in the same space. If X is normal and complete, and movable cone is of full dimension, and the rational class group, this is Q vector space. So from now on, let's assume dimension equal 2. Then Cox ring is generated by global sections supported on negative curves and global sections of Neff divisors. So you just look at kind of negative curves. Of course, negative curves has only one-dimensional space of sections. So for this ring to be finitely generated, we need to have finitely made negative curves. And also, if you pick up finite number of semi-ample divisor classes, and then you can think of all sections supported on the linear sum, non-negative linear sum of these semi-ample divisors is finitely generated. So for X to be Moriddin, X contains only finitely made negative curves, and Neff cone is generated by semi-ample divisors. So you already see being Moriddin is a very nice property. on infinitely many negative curves, and F cone is generated by semi-ample divisors. And we have equivalent condition. Cox ring is finite generated. And the second condition is effective cone and movable cone are polyhedral, rational polyhedral. And movable cone is equal to semi-ample cone. And moreover, if one of these holds, then X should be Q factorial projective. So in my first remark here, a normal projective Q factorial variety with irregular G0 and Picard number 1 is Mori dream. So Picard number 1 always Mori dream. So all cones live in one-dimensional space. You don't have to worry about it. And smooth complete intersections of high dimension have irregular G0 and Picard number 1, hence a Mori dream. And very general surfaces in P3 of degree at least 4 are Mori dream. Smooth surfaces of degree less than or equal to 3 are Mori dream. For example, Fermat cubic is Mori dream, but Fermat quartic is not. Because Fermat quartic is a KC surface with infinite automorphism group. So in case where Picard number bigger than or equal to 3, we have a very nice kind of description. And if effective cone is polyhedral, I mean rational polyhedral, then this effective cone should be generated by the classes of these exceptional curves, I mean negative curves. So one corollary is that if the Picard number is at least 3, and if number of negative curves is smaller than Picard number, then X cannot be Mori dream. So to be Mori dream, you need enough number of negative curves exceeding the Picard number. And for surfaces with Godard dimension non-positive, there have been many works for being Mori dream. So there are known results or criterion for being Mori dream. So one result given by Birka, Karsini, Heikon, Mekanan. Any log Fano variety is Mori dream. Log Fano variety was discussed by Birka this morning. In particular, weak Delpezzo surfaces and log Delpezzo surfaces are Mori dream. Here, weak Delpezzo means canonical class is big and nep. Anti-canonical class is big and nep. Delpezzo surface just anti-canonical class is ample. Here, any smooth rational surface is X with big anti-canonical class is that is Mori dream. So you don't need Nephenis or anti-canonical class. So for example, blow up of P2 at arbitrary choice of 8 points, up to 8 points are Mori dream. For rational surfaces, there is no necessary and sufficient condition. And there are many. So in general, if you blow many points, you don't get Mori dream. But even if you blow many points, but if those points satisfy certain condition, then you still get Mori dream. So Mori dream means the Picard lattice, Picard group upstairs. It's a certain quite nice structure. So blow up of the Hirzebruch surface at any number of points lying on the union of the negative curve and n+1 distinct fibers, and blow up of P2 at n+1 point, n of which lie on a conic, and the surface obtained by blowing up P2 at the 10 intersection points of 5 general lines. 5 general lines forms a pentagon, has 10 intersection points. And the surface obtained by considering 3 distinct lines, L1, L2, L3, and blowing up the 3 intersections, and 2 point on L1, 3 point on L2, 5 point on L3. So altogether, you have 13 point blow up. Still, this case is Mori dream. And finally, the surface X obtained by blowing up P2 at the 9 inflection points of a smooth cubic. But in general, I mean, if you blow up P2 at 9 general points, you don't get Mori dream. But this case is Mori dream. And also, a general rational elliptic surfaces are not Mori dream. Here, a rational elliptic surface is a blow up of P2 at the 9 M2 base points of a Halpern pencil of degree 3m. Usually, if you take n is equal to 1, you have a cubic pencil. They have 9 base points. You blow up, then you get rational elliptic surface with a section. But in this case, if n is bigger than or equal to 1, or bigger than 1, then this rational elliptic surface doesn't have a section because it has a multiple fiber. It has a unique multiple fiber with multiplicity m. Only one multiple fiber. If it has 2 multiple fibers, and then it's no longer rational surface, the Godard dimension will go up. And here, if all fibers are irreducible, this is the general case. Irreducible means smooth elliptic curve or nodal curve or cuspidal curve. Then the surface is not Mori dream. Well, for K-series surfaces and any K-surface case, we have a criterion. So, for a projective K-series surface or an any K-surface, well, a K-series surface may be non-projective, but all any K-surfaces are projective. Then X is Mori dream if and only if effective cone is polyhedral, I mean, rational polyhedral. If and only if orthorhomizing group is finite. The second equivalence coming from Torelli theorem. So for each fixed polarization, a very general K-series surface has finite orthorhomizing group, so it is Mori dream. But Kumba surfaces orthorhomizing group is infinite, and Fermat quartic also infinite orthorhomizing group. They are not Mori dream. But on the other hand, general NK surface is not Mori dream. So general NK surface has infinite orthorhomizing group. So NK surface with finite orthorhomizing group are very, very rare. Several components with kind of dimension 1 or dimension 0. And on a K-series surface, a net line bundle L is semi-ample. So we have equality among these 3 cones. Semi-ample cone is equal to movable cone is equal to net cone. Here's one example in Picard number 2 case. Picard number 2, then using binary quadratic forms, I mean, using number theory, one can show that orthorhomizing group should be one of these 3, finite cyclic, infinite cyclic, or infinite dihedral. So in the letter 2 case, X is not Mori dream. So also the orthorhomizing of infinite order correspond to a solution of Pell equation. Here is the one example. Unfortunately, this example I don't know how to put it in projective way. I don't know the equation. But okay, let's think about K3 surface X with Picard group with the less intersection form, intersection matrix 4, 2, 2 minus 4. This is equivalent to 4, 6, 6, 4. Well, such a K3 surface exists by the surjectivity of the period map. It's one part of Torelli's theorem. This one admits a free automorphism of positive entropy, which generates full automorphism group. So in this case, automorphism group is infinite cyclic. Here, X has two irreducible curves, C1, C2, generating the second intersection matrix. But no smooth rational curve. And then you can compute the effective cone, the closure of the effective cone. So you see the boundary is aligned with irrational slope. So it is not rational polyhedral. This confirms that X is not Moridt-Rim. And on the other hand, a K3 surface Picard number 2, which is Moridt-Rim, this, you can think of this, a smooth quartic surface with a hyperplane section split into two curves, one line and cubic. And you can think of this equation. The general equation is Z times cubic F3 plus W times cubic G3 equals 0. If you choose F3 and G3 general, meaning X is general, then Picard group has rank 2 generated by E and R. And in this case, effective cone also generated by E and R, and left cone is smaller than this. Both rational polyhedral, and the morphism 3H minus E contract R maps to a combinatorial minimal model of X. So X is just obtained by contracting R, which is the unique negative curve. Well, you can also think about hyperplane section is union of two conics. Same conclusion. Elliptic surfaces. Elliptic surfaces. Elliptic surface is in general, it's an elliptic surface means a genus 1 vibration. Not necessarily have a section. If X is Moridt-Rim, then there is a negative curve C, which is horizontal, but not contained in a fiber. Okay, let me skip. Let me recall the 2 elliptic surface case. If elliptic surface has two multiple fibers with multiplicity 2, then it must be an NK surface. And every NK surface has an elliptic vibration with two multiple fibers, multiplicity 2. And every NK surface admits an elliptic vibration structure, non-unique. And it is Moridt-Rim, depend on if effective cone is polyhedral, depend on if automorphism group is finite, depend on if X contains only finite number of -2 curves, smooth rational curves, and any reducible vibration is extremal. Extremal means the number of components of reducible fibers and a arbitrary multisection will generate the Picard group up to certain index. And Nikulin and Kondo classified such NK surfaces. So we know everything about NK surfaces with finite automorphism groups, so that Mori-driven NK surfaces. And so let's get back to some general theory. Pullbacks of Mori-driven surfaces. Suppose you have a surjective morphism x to y, any dimension. Then if x is Mori-driven, then so is y. So the image of Mori-driven surface is Mori-driven. But the converse is not true. So see that the below P2 at sufficiently many general points is not Mori-driven. Converse is not true even if X is a minimal smooth projective surface. The third, the example for the counterexample to third case, NK surfaces with 8 minus 2, disjoint minus 2 curves. So there are NK surfaces with infinite automorphism group and with 8 disjoint minus 2 curves. And contracting the 8 curves to get a surface Y with 8 A1 singular points, or Picard number 2. And in this case, Neph cone is equal to sine Neph cone generated by 2 isotropic vectors, because here the intersection form is orthogonal to this 8 A1 inside Picard lattice of NK surface, which is even unimodulo of sigma 219. So this is kind of hyperbolic lattice, even. So you have 2 isotropic vectors. Then you can think of it because this is Picard number 2, so they are kind of certain multiple. This is irreducible curve. Thus, Y is a Mori-driven. So a non-Mori-driven X may have a combinatorial minimal Mori-driven. But I do not know whether this also happened in the category of minimal surface of general type with PG0. Okay, so now let's say 20 minutes. Let X be a minimal surface of general type, then canonical class is Neph and big. If PG equals 0, then automatically irregular is 0, and K square can take value 1 through 9 due to Yao-Miyaoka inequality. And question is, which minimal surface of general type is 0 are Mori-driven surface? There are many examples. So the following minimal surface of general type P0 are Mori-driven surface, and their effective cones are computed explicitly. So all fake project planes, they are Mori-driven because they have Picard number 1. And surfaces with K-square equal 8, PG0, which are isogenous to higher products of unmixed type. So this is just the quotient of 2 curves of high genus by a free group, but with PG0. And in OS surfaces and Chen surface, Ifan Chen, and Kulikov surfaces and Brunner surfaces, and product quotient. This is kind of generalization of this, the second case. Now you allow kind of not free action, fixed point, and then you get certain singularities and you resolve. And the last one is also. So we have many examples. Classically, almost all classical examples are Mori-driven. So let me say, so word about the case calculate. Well, in this case, Picard number is 2. So if it doesn't have any negative curve, then you cannot contract further. Then you cannot contract. So the question is whether it is a molydrin itself. So numerical group, which is Picard group modulo torsion, or in this case, second integral cohomology group modulo torsion, is unimodular, indefinite of rank 2. And all known examples are free quotient of the product of two upper open planes. So gamma is a subgroup of automorphism group of product of two upper open planes or unit disk. And this is nothing but extension by 2 of PSL2R squared. If gamma is irreducible, then get the one type is the so-called Chabel type surfaces. Chabel constructed such examples. Gamma is reducible, then the examples are isogenous to higher product of one mixed to a mixed type. Well, what is irreducible? What is reducible? Reducible means gamma has image on PSL2R. Most PSL2R are discrete. But irreducible means gamma has non-discrete image inside PS2R. So irreducible case is quite non-geometric. We cannot see much, but it exists by number theory. And also, these surfaces are interesting in view of Hirzebruch's question. Is there an exotic P1 cross P1 or 1 point blob of P2? Exotic means homeomorphic, but not isomorphic, not diffeomorphic, or not symplectomorphic. But in any category, we don't know any such example. So general conjecture is that this surface is entitled, it should have universal cover product of two upper planes. Then Hirzebruch question is negated. Here, let me say a few words more on Chabel type surfaces. Okay, and Chabel type surfaces are kind of first examples which are not molydrin. Chabel, in her paper, a class of algebraic surface of general type constructed from quaternion algebras, presented surface of general type with k square equal 8, pg equal 3 equal 0. They are free co-compact quotient by a group gamma. But in her case, gamma is not just the subgroup of PSL2R, but it also has a lifting to SL2R. And this is kind of key factor we used to prove that they are not molydrin. Such a surface is an even Faker quadrid without the negative curve. So anyway, this is a kind of unmixed action. So upstairs you have already product structure. So downstairs you still have product structure. So there are two divisors with self-intersection 0. But the question is whether they are effective or not. If they are not effective, then they are not molydrin, because this is left cone, also closure of effective cone. So recently, 카타나제 카시니 typo, it should be K. They are not molydrin. Any modular form corresponding to the divisor. Here, L1, N0 means a kind of one side vertical. divisor, real divisor. Suppose, well, actually the tangent bundle also split can be proven to be identically zero by the density argument, by the density of gamma inside PSL2R, density inside SL2R also. For infinitesimal prime P, the reduction mod P is a smooth surface defined over algebraic cross field of characteristic P with k square equal 8 is Moridt-Rim. And on SP, there are two negative divisors. Both are effective. So SP must have two distinct negative curves of type -1a, the other type b -1. I mean, here we still have hyperbolic lattice of rank 2. So this is the notation. And they generate effective cone of SP. So in characteristic 0, it looks like this is so, but this boundary is not effective. Yeah? So this is but in over P, you have two negative curves. Generated by two negative curves. So that left cone gets smaller. And left cone is also polyhedral. It's also orthogonal to this, and also orthogonal to this. So reduction mod P, you get Moridt-Rim. So in general, you see, given variety, reduction mod P, you'd get more curves. Yeah, that's just my remark here. Reduction mod P may increase Picard number. For example, Fermat-Cortic surface. Fermat-Cortic surface has Picard number 20, but reduction mod P, the Picard number could jump to 22. But K3 surface case, PG equal 1. Second Betti number is 22. But for our case, PG equals 0. So Picard number doesn't jump, but still you get more negative curves. So the Chabel type surface has no negative curve over complex number field, but it has two negative curves in suitable reduction mod P. Yeah, reduction mod P equal congruent to 3 mod 4 has Picard number 22 called super singular K3 surfaces. Okay, so let me skip Inoue case. This is even simpler than Brunier case at the beginning I discussed. Godot surfaces, let me, okay. Well, I started 10 minutes later, but I want to keep you on time, so I'll try to finish it in 5 minutes. So no example with k-square that is Moridt-Rim or that is not Moridt-Rim. There are many candidates, Barlow surfaces and classical Godot surface. Well, examples of non-minimal surface of general type is PG0, which are not molybdenum. Of course, if you blow up minimal surface of general type, then you expect which is not molybdenum. So this is explicit example we have. And as I mentioned before, molybdenum implies Q factoriality and projectivity. Okay, so here's the my conclusion on combinatorial minimal models of molybdenum surfaces. That X be a molybdenum surface, then one can contract some negative curves from X to obtain a normal molybdenum surface X naught with Picard number n most 2 that does not allow further contraction. And X naught is called a combinatorially minimal model of X. And X naught is projective and Q factorial and molybdenum. And number 3, if the Picard number is 2, then X naught has a finite morphism to P1 cross P1. And number 4, conversely, if Z is a normal projective Q factorial regular surface, meaning that irregularity is 0, with either Picard number 1 or Picard number 2 having a finite morphism, then Z is a molybdenum. And Z itself is a combinatorial minimal molybdenum surface. So this is a kind of general theorem. And then let me answer how many singular points and also what kind of singularities the molybdenum combinatorially minimal. Why we call combinatorial? Well, even in higher dimension, you can have also combinatorial minimal model. You have a map, but the map is not just morphism. Sometimes it intertwined with alternated with small modification, like a flip, flip and then contraction, flip, contraction, and so on. But in dimension 2 case, we don't have small contraction. We just contract a small modification. So what they call is like a kind of small Q factorial modification and ambient neat modification. The combination of this will lead to a combinatorial minimal model in higher dimensions. But in dimension 2, we just contract. And then what kind of singularities you have? Here, then I can answer some partial answer when the minimal model has only quotient singularities. There are many examples with quotient singularities. Let X0 be a combinatorial minimal molybdenum surface having at worst quotient singularities. Suppose that the minimal resolution is a minimal surface of general type with PG0. Then there are only finitely many singularity types X0 can have. So the list is finite. And furthermore, if the Picard number is equal to 1, then number of singular points is bounded by 4. And if the number is equal to 4, then the singularity type is 4A2 or 2A2 plus 2A3. Both supported by examples. And if Picard number 2, then the bound is 6. And if the number of singular points is 6, then the singularity type is 6A1. 6A1 means 6 points of A1 type singularity. Or 4A1 plus A2 plus 1/3 of 1, 1. So both cases also supported by examples. If the singularity number of singular points is equal to 5, then the possible singularity type is still 2, 3A1 plus 1/4, 1, 1, 1/8, 1, 5. They're all cyclic singularities. We didn't assume that cyclic singularities, but just the quotient singularities. Actually, if the number of singular points is rather big, then no non-cyclic singularity can appear. So Q homology P2, our X0, if it has picard number 1, is a Q homology P2. Q homology P2 means a normal projective surface with same Betti numbers as P2. So first Betti number 0, second Betti number 1, third Betti number 0. So same Betti numbers as P2. And for any non-necessarily general type, whatever, with quotient singularities, then we have a bound by 5. And if the number of singular points is 5, then the minimal resolution is an Ehrlich surface. So, well, from this, we get kind of the first result. We are working with general type. And also examples of combinatorial minimal model with 4A2 singularities. Well, this is only example I know. They are coming from fake project planes. There are fake project planes with automorphism group, 3 elementary group of order 9. Any quotient has 4A2 singularities and picard number 1 and k square equal to 1. And its minimal resolution is a numerical Bordeaux surface with picard number 9 and k square equal to 1. Okay, this is my final slide. I finished my talk with question. And what kind of singularities on combinatorial minimal models? Can a minimal surface of general type with PG0 have a combinatorially minimal model with only log canonical singularities or slightly general Dubois singularities? Almost all known examples have a combinatorial minimal model with only log canonical singularities. Many examples with only quotient singularities, and also Brunel surface we saw 3 simple elliptic singularities, and simple elliptic singularities are canonical, low canonical. So no counter example yet. Okay, let me stop here. Thank you for your attention.
So, any questions? Okay, so I have a question. But in high dimension case, for combinatorial situation,
yeah, I mean, we don't have this kind of structure theorem. Yeah, but maybe you can guess that like yeah, P1 cross P1 cross P1, finite morphism, or P2 cross P1, or something. So a bit more, yeah. Maybe the 3-dimensional case might be yeah, next interesting case. But of course, you have to work with the flips, so it's more complicated.
More complicated.
Yeah.
Okay, so if no further question, let's thank our speaker again.
Okay, thank you.